An object from another star system just accelerated near our sun without leaving a trace. No exhaust, no debris, just motion born of nothing. If confirmed, this single observation could force us to rewrite the laws of motion, admit our physics is incomplete, or confront the possibility that something intelligent is traveling through our cosmic neighborhood. NASA's astrometry shows a 4 arcsecond positional offset measurements checked and rechecked. The math demands 5 billion tons of ejected material, yet telescopes see silence. So where did the debris go? And if it never existed, what pushed this comet off course? Tonight, we explore the 10th anomaly of interstellar comet 3I Atlas discovered July 2025. 9 confirmed oddities already make this the strangest visitor from beyond our solar system. But the 10th, the acceleration without cause, threatens to unravel everything we thought we knew about how objects move through space. December 19, 2025 will bring answers. The question is, are we ready for them? Stick with me as we journey through the data, the speculation, and the profound implications of an object that refuses to follow the rules. Because this story is still unfolding in real time.
July 1st, 2025. A telescope in Chile captures a faint streak of light moving through the constellation Aquarius. The Asteroid Terrestrial Impact Last Alert System ATLAS, for short, is designed to find near-Earth objects. Asteroids that might pose a threat to our planet. But within hours of the first observations, astronomers realize they're looking at something fundamentally different. The orbit is wrong. The speed is wrong. The trajectory curves in a way that says this object didn't come from our neighborhood. They run the numbers again, checking for errors. They call in confirmations from other telescopes around the world. Amateur astronomers join the effort. Professional observatories repoint their instruments, and by the end of the week, it's official. Hyperbolic trajectory, interstellar origin. The third such object ever confirmed in the history of astronomy. The designation is assigned 3I Atlas. The I stands for interstellar, a cosmic passport stamp that says, not from around here. The 3 indicates it's the third confirmed visitor from beyond our solar system, following 1I Oumuamua in 2017 and 2I Borisov in 2019. But unlike Borisov, which behaved like a well-mannered comet and gave astronomers a sense of relief that the universe still made sense, 3I Atlas immediately begins showing signs of strangeness. Its path is retrograde, moving opposite to the rotation of the solar system. That's not unusual for an interstellar visitor. There's no reason an object from another star should care about which way our planets orbit. But here's what is unusual. The orbit is nearly aligned with the ecliptic plane, the flat disk where Earth and the other planets circle the Sun. Think about it this way. Space is three-dimensional. Objects can come from any direction, up, down, sideways, at any angle. The ecliptic plane is just one thin slice through that three-dimensional space. The probability that an object arriving randomly from interstellar space would align closely with that plane is remarkably low. About 0.2%, 1 in 500. Not impossible, but uncomfortably improbable. Within the first week of observations, spectroscopy reveals another oddity. The object is producing a coma, that fuzzy envelope of gas that distinguishes comets from asteroids. But the gas ratios are off. Way off. Carbon dioxide dominates, something we'll explore in detail later. For now, what matters is that from day one, 3I Atlas is not behaving like a typical comet. The object is moving fast. About 61 kilometers per second relative to the Sun when discovered. That's 137,000 miles per hour. At that speed, you could circle Earth's equator in less than 3 minutes. It's the speed of something that's been traveling through the void between stars for possibly millions of years, carrying momentum from whatever event ejected it from its home system. Size estimates come in from multiple instruments. The Hubble Space Telescope gets the clearest images. The nucleus, the solid core of the comet, appears to be somewhere between 0.44 and 5.6 kilometers in diameter. That's a huge range reflecting our uncertainty. It could be as small as 4 football fields, placed end to end, or as large as a small mountain. The uncertainty comes from not knowing the reflectivity of the surface. Dark objects appear smaller than bright objects at the same distance. Without knowing how much sunlight is reflected versus absorbed, we can only bracket the possibilities. But even taking the conservative middle estimate, we're looking at an object massive enough to carry serious momentum. This isn't a pebble. This is billions or trillions of tons of rock and ice traveling at speeds that make bullets look stationary, and it's heading inward toward the sun. The trajectory calculations show a perihelion date, the closest approach to the sun, of October 29, 2025. That's just 4 months away from discovery. The object will pass about 203 million kilometers from the sun, roughly 1.36 astronomical units. For reference, that's between the orbits of Earth and Mars. Close enough that solar heating will activate any volatile materials on or near the surface. Close enough that if this is a comet, and the coma suggests it is, we should see spectacular displays of outgassing and dust production. Think of it like this. Imagine a massive ice sculpture sitting in the freezing vacuum of space for millions of years, never experiencing warmth, preserved in pristine cold. Then suddenly it falls toward a furnace. The sun's radiation begins to penetrate the surface. Molecules that have been locked in solid form since before our solar system existed start to vibrate, to move, to break free. The ice doesn't melt, it sublimates, transitioning directly from solid to gas, bypassing the liquid phase entirely. This process is violent. Trapped pockets of gas can build pressure beneath the surface, leading to explosive venting. The nucleus can crack, revealing fresh layers of material. Jets can erupt from active regions, shooting material into space at hundreds or thousands of meters per second. For a typical comet, this is when the show begins. When it transforms from a dim, distant speck into something naked, eyes can see a glowing visitor with gossamer tails streaming behind it, a wanderer from the outer darkness temporarily catching fire in the sun's embrace. 3i Atlas should follow this script, should transform as it falls sunward. And indeed, the early observations suggest activity is beginning. The coma is growing. Spectroscopy detects gases escaping. The object is waking up. But something about how it's waking up will turn out to be wrong. Something about the proportions, the ratios, the physics of thrust and debris. Something that won't become clear until October, when the measurements come in and astronomers start doing the math. But there's something else about the timing that catches attention. The perihelion passage will occur just 8 days after solar conjunction, the moment when the object passes directly behind the sun as viewed from Earth. During solar conjunction, telescopes on Earth can't observe the object. The sun's glare overwhelms everything nearby. It's an observational blackout that will last about 2 weeks in late October, which means the most interesting part of the object's journey, its closest approach to the sun, when comets typically become most active, will happen while Earth-based telescopes are effectively blind. Coincidence? Probably. The sun is large, and any object passing close to it will inevitably spend some time hidden from Earth's perspective. It's a simple consequence of geometry. If you draw a line from Earth to the sun and an object crosses near the sun, there's a period when it's lost in the glare. This happens to many comets. It's not unusual, but the timing is noted, filed away, a detail that will become more significant later. Because here's what makes it interesting. If you were planning to do something near the sun, some maneuver, some adjustment to your trajectory, and you didn't want Earth-based observers to see it, clearly you'd time it exactly like this. You'd wait for conjunction. You'd act when the sun itself serves as a shield, when scattered light drowns out faint signals, when tracking becomes impossible. Nature doesn't plan, of course. Natural objects don't care about observation windows. But the human mind, trained to look for patterns, can't help noticing when circumstances align in convenient ways. When the timing seems fortuitous, it's probably nothing, Just one more low-probability event in a universe full of low-probability events. But add it to the list. Anomaly noted, question raised. We'll return to this point when we discuss all 9 anomalies together and how they might be connected. Throughout July and August 2025, observatories worldwide track 3i Atlas. The James Webb Space Telescope dedicates time to spectroscopic analysis. Hubble continues imaging to refine size estimates. Ground-based telescopes with adaptive optics monitor brightness changes. Radio telescopes like ALMA measure positions with extraordinary precision. The data accumulates. And with each new observation, with each new spectrum and image and positional measurement, the oddities multiply. The object is not just unusual, it's anomalous in multiple independent ways. Ways that individually might be dismissed as edge cases or measurement uncertainties, but together begin to form a pattern. A pattern that suggests 3i Atlas is unlike anything we've seen before. A pattern that will culminate in a 10th anomaly so troubling that it calls into question our fundamental understanding of how objects move through space. But before we get to that, we need to understand the 9 anomalies that came first. The 9 ways this object is already breaking the rules.
Let's walk through them systematically, starting with what we can measure most precisely where this object came from and where it's going. Anomaly 1, the ecliptic alignment. We've already touched on this, but it deserves deeper examination. The ecliptic plane is significant because it's where all the major planets orbit. It's where most of the solar system's mass and activity is concentrated. If you were designing a trajectory to survey the inner solar system to pass near interesting worlds and study the sun up close, you'd naturally aim for the ecliptic plane. The problem is, 3i Atlas shouldn't be designed. It should be a random chunk of ice and rock ejected from another star system billions of years ago, wandering through the galaxy with no particular destination. Random trajectories should come from random directions. Yet 3i Atlas's orbit aligns to within 5 degrees of the ecliptic. Some astronomers argue this is selection bias. Survey telescopes like Atlas spend most of their time scanning the ecliptic region because that's where near-Earth asteroids are found. So naturally, we're more likely to detect interstellar objects that pass through that region, even if they're no more common than objects arriving at other angles. That's a valid point, but even accounting for survey bias, the degree of alignment remains surprisingly precise. It's in the tail end of the probability distribution. Not impossible, but sitting uncomfortably close to the edge of what chance alone would produce. Anomaly 2. The planetary encounters. Track. 3i Atlas's path through the inner solar system and something else emerges. On October 4, 2025, it passes relatively near Mars, not a collision, not even a particularly close approach by cosmic standards, but near enough that Mars's gravity perturbs the orbit slightly. Less than a week later, on October 10th, it swings by Venus. Then perihelion on October 29th.
Then, as it heads back outward, it passes near Jupiter's orbital region in early November. 4 significant solar system bodies encountered in rapid succession. Researchers have run Monte Carlo simulations, generating thousands of random interstellar trajectories and seeing how many happen to pass near multiple planets within a short time frame. The numbers depend on how you define near, but for reasonable definitions, within distances where gravitational influence is measurable, the probability comes out to roughly 0.005%, 1 in 20,000. Stack that on top of the ecliptic alignment. Multiply 0.2% by 0.005%, you get 0.001%, 1 in 10 million. These are not comforting odds. They don't prove anything sinister, but they raise an eyebrow. They make you wonder if you're watching a coin flip or a magic trick. Anomaly 3. The conjunction timing. We mentioned this earlier. Perihelion occurs just 8 days after solar conjunction, placing the object behind the Sun from Earth's perspective during its most active phase. From mid-October through early November, Earth-based telescopes can't get a clear view. Space-based observatories closer to the sun, solar monitoring satellites, can still observe, but they're not optimized for tracking comets. They're designed to watch the sun itself. The timing hides the object during the exact period when it should be most dramatic, most active, most interesting. If you wanted to perform a maneuver near the sun without being watched from Earth, you'd time it exactly like this. But again, the sun occupies a large portion of the sky. Any object passing close to it will be unobservable for some period. The fact that perihelion coincides with conjunction might be nothing more than geometry. Still, it's filed as Anomaly 3, a detail that fits a larger pattern. Anomaly 4, the composition reversal. Now we move from orbital mechanics to chemistry, and this is where things get truly strange. The James Webb Space Telescope's infrared instruments analyze the light coming from 3I Atlas's coma in August and September 2025. When you split that light into its component wavelengths, you see dark absorption lines where specific molecules soak up specific colors. It's a chemical fingerprint. What Webb found is a comet with a carbon dioxide to water ratio of approximately 8:1, 8 times more carbon dioxide than water. For context, typical solar system comets are water dominant. Water ice is the primary volatile, usually accounting for 80% or more of the ices. Carbon dioxide is present but minor, perhaps 10 to 20%. The ratio is usually 10:1 or 101 in favor of water, not the other way around. 3I Atlas flips this completely. It's a carbon dioxide comet with a little water mixed in. That's backwards. That's wrong. It suggests formation in an environment radically different from anything in our solar system. Why does this matter? Because water ice is the most common volatile in the outer solar system. Oxygen is the third most abundant element in the universe, after hydrogen and helium. Hydrogen and oxygen combine easily, and water ice is stable over a wide range of temperatures and pressures. It's the default building block of comets. Carbon dioxide is less common because carbon is less abundant than hydrogen, and because CO2 ice sublimates turns directly from solid to gas at higher temperatures than water ice. For an object to be carbon dioxide rich, it must have formed in a very cold, carbon-rich environment where water was suppressed. Perhaps a molecular cloud far from any star or a protoplanetary disk with unusual chemistry. Such environments exist in theory, but we've never seen a comet from one. Until now.
Anomaly 5, the water deficit. Related to Anomaly 4, but worth stating separately. 3I Atlas has only about 4% water by mass, 4%. Most comets are often described as dirty snowballs, primarily ice with some rock and dust mixed in. 3I Atlas is more like a dirty carbon dioxide ball, with barely any water at all. This has implications for how the object formed and where it came from. It also has implications for how it behaves as it approaches the sun. Water ice sublimates vigorously when heated, producing the spectacular tails and comas we associate with comets. Carbon dioxide also sublimates, but differently. It transitions from solid to gas at lower temperatures and doesn't drag as much dust along. A water-poor, carbon dioxide-rich comet should behave differently than a normal comet. It should be less dusty, more gas-dominated, possibly less visually spectacular, despite being active. Keep that in mind. It becomes relevant when we discuss the 10th anomaly. Anomaly 6. The polarization signature. When light bounces off a surface or scatters off particles, it becomes polarized, meaning the light waves align in a particular orientation. The degree of polarization depends on the size, shape, and composition of the particles. Doing the scattering as well as the viewing angle, astronomers measured the polarization of sunlight reflected by 3I Atlas and found something unprecedented: extreme negative polarization. A minimum of about 2.7% at a phase angle of 7 degrees. I know that sounds technical. Here's what it means in plain language. The particles in the coma are scattering light in a way we've never seen before from any comet. The polarization signature doesn't match silicate dust, doesn't match organic grains, doesn't match any known mixture of cometary materials. It's a fingerprint with no match in the database. One explanation is that the particles are extremely small, smaller than the wavelength of visible light.
Another is that they're made of materials with unusual refractive properties. Pure carbon dioxide ice grains might produce such a signature, or perhaps some kind of organic polymer formed by cosmic ray bombardment during millions of years in interstellar space. Whatever the cause, the polarimetry is waving a red flag. This object's surface or coma particles are not like those of any solar system comet. Anomaly 7. The explosive brightening. Between August and October 2025, as 3I Atlas approached perihelion, its brightness increased dramatically, far more dramatically than expected. Comets brighten as they approach the sun. That's normal. The closer they get to the heat source, the more ice sublimates, the more sunlight they reflect. Brightness typically scales as a power law with solar distance. You can predict the curve with reasonable accuracy for most comets. 3I Atlas didn't follow the curve. It brightened by several magnitudes in a matter of weeks.
The kind of brightening you see during a fragmentation event when the nucleus breaks apart and exposes fresh ice to sunlight. But there's no evidence of fragmentation. The nucleus appears intact. So what's causing the rapid brightness increase? Several solar observatories. Stereo Soho GOES 19 watched the object as it neared the sun. All reported the same thing, unprecedented brightening, happening faster than any known comet. This suggests either an enormous increase in surface activity or a fundamental difference in how this object responds to solar heating. Anomaly 8. The blue color. Here's where it gets really backwards. Comets are typically reddish, especially close to the sun. Dust dominates the reflected light, and dust silicates organics. Iron oxides tends to absorb blue wavelengths and reflect red. 3I Atlas turned blue, bluer than the sun itself. Blue light suggests you're reflecting or emitting in the shorter wavelengths. This could mean the coma is gas-dominated rather than dust-dominated. Fluorescence from ionized carbon dioxide glows in specific blue wavelengths when excited by solar ultraviolet radiation. Or it could mean the surface is highly reflective and fresh, like clean ice rather than dirty rock. Freshly exposed ice scatters short wavelengths, efficiently producing a bluish tint. Either way, it's the opposite of what should happen. Comets redden near the sun. 3I Atlas bluens. That's backwards. That's wrong. Anomaly 9. The anti-tail comet tails point away from the sun. Always. That's basic physics. Solar wind and radiation pressure push gas and dust outward, creating the characteristic tail streaming behind the comet as it moves through space. This is one of the most fundamental observations about comets known for centuries. Even ancient civilizations noticed that comet tails always point away from the sun, regardless of which direction the comet is moving. It's not like the trail of smoke behind an airplane which points backward along the direction of motion. It's a structure shaped by the sun's influence, always pointing radially outward from our star. The solar wind, a constant stream of charged particles flowing from the sun at hundreds of kilometers per second, pushes ionized gas into what we call the ion tail, or type 1 tail. This tail is typically straight blue in color due to fluorescence from ionized carbon monoxide and can extend millions of kilometers into space. Solar radiation pressure. The physical momentum carried by photons pushes dust particles into what we call the dust tail, or type 2 tail. This tail is typically curved yellowish in color because it's just reflected sunlight from dust grains, and follows the comet's orbital path because dust particles have inertia and don't respond as quickly to the sun's push as gas does. Both types of tails point away from the sun. It's a rule written in the laws of physics.
Light and particles moving outward from the sun carry momentum. When they hit gas and dust around a comet, they transfer that momentum pushing material in the anti-solar direction. Simple, universal, inviolable, except when it isn't. In July and August 2025, before perihelion, observers reported what appeared to be a sun-facing jet, an anti-tail. Material being ejected toward the sun, or at least in a direction that doesn't follow normal geometry. Now, astronomers have seen apparent anti-tails before. Sometimes they're optical illusions, tricks of geometry. If you view a comet's dust tail edge-on, if your line of sight happens to align with the plane of the tail, you can see the near side of the tail appearing to point toward the sun while the far side points away. Your brain, trying to make sense of the perspective, can be fooled into thinking there's a tail pointing the wrong way. This happens often enough that experienced comet observers know to be skeptical. They check the viewing geometry model, the three-dimensional structure, and usually find that what appeared to be an anti-tail is really just a normal tail seen from an unusual angle. But in this case, multiple independent observations from different viewing angles suggest the jet is real. The geometry has been checked, the three-dimensional models have been run, and the conclusion is troubling material appears to be ejected in a direction that standard comet physics can't easily explain. How could this happen? A few possibilities. The nucleus might be rotating rapidly, and active regions, spots where ice is sublimating and producing jets, might be positioned on the sun-facing side. If gas is being blasted out from the day side with enough velocity, it might overwhelm the radiation pressure that would normally push it away, at least for a short distance before the sun's influence takes over. Or there might be some kind of shadowing effect. Perhaps the nucleus has an irregular shape with cliffs or ridges that cast shadows, and active regions in those shadows produce jets at odd angles. When ice sublimates in a shadowed region, the gas doesn't immediately feel the full force of solar radiation, so it can escape in directions that seem wrong. Or maybe, and this is where speculation begins, the jets aren't driven by solar heating at all. Maybe they're controlled, directed, produced by some internal process that doesn't care about the sun's geometry because it's not responding to the sun's heat. If 3I Atlas were venting stored gas deliberately using internal reservoirs and valves rather than relying on surface sublimation, you might see jets pointing in arbitrary directions. Toward the sun, away from it sideways, whatever direction produces the desired thrust. This is, of course, the artificial hypothesis creeping in. Natural comets are slaves to thermal physics. Heat comes from the sun. Ice sublimates on the sunward side jets follow predictable patterns. An engineered object might not follow those patterns. It might use its stored volatiles strategically firing jets in whatever direction adjusts its trajectory optimally. I'm not saying that's what's happening. I'm saying the observation is weird enough that it invites these kinds of thoughts. And when you stack this weirdness on top of all the other anomalies, the trajectory, the composition, the brightening, the polarization, the pile becomes hard to ignore. Jets that don't point anti-solar are rare, but not unheard of in natural comets. They can happen. But they require special circumstances, unusual configurations, edge cases. And 3I Atlas seems to collect edge cases the way other comets collect dust. So those are the 9. 9 separate, independently measured anomalies. 9 ways 3I Atlas violates expectations. Individually, each could be explained. Unusual but natural. Edge cases.
The universe is vast and full of variety. With enough objects, rare things will happen. But collectively, 9 low-probability features on a single object. That's when you start wondering if you're looking at a coincidence or a pattern, when you start asking whether these anomalies are independent random events or symptoms of something deeper. And then came the 10th, the one that ties all the others together and makes them terrifying.
October 2025. The Atacama Large Millimeter Submillimeter Array ALMA, one of the most precise astrometric instruments on Earth, tracks 3I Atlas as it approaches perihelion. Astrometry is the art of measuring where things are in the sky with absurd precision. ALMA consists of 66 radio dishes working together in the Chilean desert, creating an effective telescope the size of a city. When pointed at a small moving object, it can pin down that object's position relative to background stars and quasars to within fractions of an arc-second. For context, an arc-second is 1/3/600th of a degree. It's roughly the apparent size of a quarter viewed from 4 kilometers away. Measuring to fractions of an arc-second is like measuring the width of a human hair from across a football field. ALMA observes 3I Atlas near perihelion and compares its measured position to the predicted position. The prediction comes from gravitational models accounting for the sun's gravity, the planet's gravity, relativistic corrections, everything we know about how objects move through space. There's a mismatch, about 4 arc-seconds. 4 arc-seconds doesn't sound like much, but in astrometry it's enormous. It's a canyon. It's the difference between we know exactly where this object should be and something is pushing it off course. The measurements are checked, rechecked, compared against other instruments. Multiple independent observations confirm the offset. It's real, and when you plug that 4 arc-second positional deviation into dynamical models, when you try to figure out what force could cause that level of deviation over the course of a perihelion passage, you get a number that should make your stomach drop. Non-gravitational acceleration. The object is speeding up or changing direction in a way that requires a force beyond gravity. And the only natural explanation for such a force, the only mechanism we know of that regularly accelerates comets, is outgassing. Here's how it works. Comets are made of ice and rock frozen together. When they get close to the sun, heat vaporizes the ice. Water ice, carbon dioxide ice, methane, ammonia, all the volatile materials start boiling off. That gas drags dust with it. You get jet's tails, a glowing coma, and you get thrust. It's Newton's third law. The material flying off in one direction pushes the comet in the opposite direction. Every comet that approaches the sun experiences this. It's Rocket Propulsion 101 Comet Edition. Picture a balloon releasing air. The air rushes out one end, and the balloon shoots off in the opposite direction. That's the principle. The comet doesn't have an engine or a nozzle, but it doesn't need one. The sun's heat is the engine. The sublimating ice is the propellant. The jets are the nozzles. It's a natural rocket, crude but effective. This process has been observed and measured for centuries. Edmund Halley predicted his namesake comet would return, based partly on understanding these non-gravitational forces. Modern astronomers routinely account for outgassing when calculating comet orbits. It's standard, it's expected, it's well understood. The question is scale. How much material do you need to eject to produce a given acceleration? That depends on the comet's mass, the speed of the ejected material, the geometry of the jets. But for an object the size of 3I Atlas estimated at 50 million tons, using middle-range assumptions traveling at the speed it's traveling, deviating from its predicted path by 4 arc-seconds over the course of perihelion passage, the numbers are not ambiguous. You need massive mass loss, not a little, a lot. The calculations vary depending on assumptions, but even conservative estimates put the required ejected mass at around 5 million tons. That's about 10% of the comet's total mass lost in a matter of weeks. To put that in perspective, imagine a mountain the size of Mount Fuji suddenly vaporizing and scattering into space. That's the scale we're talking about. Billions of tons of material transformed from solid to gas, expanding outward at supersonic speeds, creating a cloud that should be visible across millions of kilometers. Other models using different assumptions about ejection velocity and jet geometry push the requirement up to 5 billion tons. Yes, billion with a B. The uncertainty is huge because we don't know the exact details of how the outgassing occurred. Were the jets collimated, focused in narrow beams, or diffuse? Was the material ejected at high velocity or low? Did it all happen at once or gradually over weeks? These details matter enormously for the calculation. But here's what we do know: whether it's 5 million tons or 5 billion tons, that scale of mass loss is not subtle.
It's not invisible, it's spectacular. But here's what we do know: whether it's 5 million tons or 5 billion tons, that scale of mass loss is not subtle. It's not invisible, it's spectacular. When a comet ejects millions or billions of tons of material, you see it. You see massive tails stretching across the sky. You see brightness spikes that persist for weeks. You see a debris cloud glowing in reflected sunlight and thermal emission visible from telescopes on Earth and in space. So where is it? Where's the debris cloud? Where's the massive tail? Where's the photometric signature of all that material being blasted into space? Some observations show increased activity. Yes, some show jets. Yes, some show brightness changes. Yes. But nothing close to what you'd expect for millions or billions of tons of mass loss. Not even in the ballpark. There's a mismatch, a profound, troubling mismatch between the observed acceleration and the observed debris. Force without visible cause.
Acceleration without the reaction mass to explain it. Let me put it another way. Imagine you're watching a rocket launch. The rocket lifts off, accelerates, climbs into the sky. You know exactly how this works. The rocket burns fuel, ejects hot gas out the back, and the reaction pushes the rocket forward. You see the flame, you see the exhaust. It makes sense. Now imagine the rocket lifts off, accelerates, climbs into the sky, but no exhaust comes out. No flame, no smoke, no gas. Just the rocket moving upward, gaining speed. You'd lose your mind. You'd check your instruments. You'd wonder if you were hallucinating, because thrust without exhaust is not how physics works. That's what we're potentially seeing with 3I Atlas. Thrust without exhaust. Or at least exhaust so faint or so hidden that we can't detect it. And that's the 10th anomaly. That's the one that makes even the calmest scientist uneasy. Let's talk about momentum. Not the motivational poster kind, the physics kind. Momentum is mass times velocity. If you want to change your momentum, you need to apply a force. And if that force comes from ejecting material like a rocket or a comet outgassing, then the momentum you gain equals the momentum of the stuff you throw away. Conservation of momentum. It's one of the iron laws of physics. You can't cheat it. You can't negotiate with it. It just is. When we say 3I Atlas underwent non-gravitational acceleration, what we're really saying is that something changed its momentum in a way gravity alone can't explain. And when we calculate how much material would need to be ejected to produce that change, we run headlong into a number that doesn't make sense given what we're seeing. Here's the setup. The object has an estimated mass somewhere between 10 billion and 100 billion kilograms. That's a rough estimate because we don't know the density or exact size. But let's use a middle ground figure: 50 billion kilograms, 50 million tons. That's a decent-sized comet nucleus. The observed positional offset near perihelion is about 4 arcseconds. Over the course of the perihelion passage, accounting for orbital dynamics, that offset corresponds to a velocity change of roughly 5 meters per second. That might sound small. 5 meters per second is about 11 miles per hour walking speed. But when you're talking about an object with a mass of 50 million tons, even a small velocity change requires an enormous momentum transfer. When a comet outgases the material it ejects has a certain velocity relative to the nucleus. For typical comet jets, that velocity is somewhere in the range of a few hundred to a few thousand meters per second. Let's assume 1,000 meters per second, a reasonable middle estimate for gas escaping from a heated surface. So if you want to change the velocity of a 50 million ton comet by 5 meters per second, and the ejected material is moving at 1,000 meters per second in the opposite direction, you need to eject about 250,000 tons of material. Wait, that's not 5 million or 5 billion. What gives the devil is in the assumptions. That calculation assumes perfect efficiency. All the ejected material, goes in exactly the opposite direction of the desired velocity change. But real comets don't work that way. Jets spray out in multiple directions. The nucleus rotates, turning jets on and off. Material goes sideways backwards in random directions that partially cancel out. When you account for realistic geometries, jets that aren't perfectly aligned rotation that averages the thrust, the required mass loss goes up dramatically. Depending on how inefficient the process is, you might need 10 times more material, or 100 times, or 1,000 times. That's how you get from 250,000 tons to 5 million, or even 5 billion tons. It all depends on the efficiency of the thrust, which depends on details we don't observe directly. But here's the key point: even the lower estimates represent enormous mass loss. An enormous mass loss produces visible effects. Let's compare with historical examples. Comet Hale-Bopp, one of the most active comets in modern history, ejected roughly 10 million tons of dust and 100 million tons of gas during its perihelion pass in 1997. The debris cloud was enormous, visible to the naked eye for months, tails stretching tens of millions of kilometers. If 3I Atlas ejected 5 billion tons, that's 50 times more than Hale-Bopp. It should be one of the most spectacular comets ever recorded. If it ejected 5 million tons, that's still on par with a major comet. We should see dramatic tails, extended comas, brightness spikes. Yet the observations show activity that's elevated but not extraordinary, present but not spectacular. The photometric brightness is higher than baseline, but not by factors of 50 or 100. The tail is visible but not massive. The spectroscopy shows outgassing, but not a catastrophic venting event. The mismatch is undeniable. Force without proportional debris, acceleration without commensurate mass loss. There are ways this could resolve. Maybe we're looking at the wrong time. Maybe the debris cloud exists, but hasn't become visible yet because the particles haven't spread out enough or haven't moved into favorable viewing geometry. Maybe the debris is there, but dark, mostly gas rather than dust, and gas doesn't reflect much sunlight. Maybe the particles are too small or too transparent to show up in our instruments. Maybe the mass was ejected in a brief, intense burst, and the cloud is still expanding, not yet luminous enough to detect from Earth. These are all possibilities, but each requires special pleading. Each requires us to invoke a scenario that, while not impossible, sits at the edge of the plausible. And with each new observation, with each new spectrum and image coming in from telescopes around the world, the window for "we just haven't seen it yet" narrows, which leaves the other option, the uncomfortable one, the one that says maybe the object accelerated without shedding the mass we expect. Maybe it's doing something we don't understand. Maybe the rules are different for this visitor from another star system. And if that's true, then the question becomes, what else is different? What else have we gotten wrong? Because an object that can change its motion without the expected reaction mass isn't just a scientific curiosity. It's a challenge to the foundation of how we understand motion, momentum, and the behavior of matter in space. It's the kind of anomaly that either revolutionizes a field or breaks careers trying to explain it. Let's paint a picture of what 5 billion tons of ejected material looks like in space. Imagine every drop of water in a lake the size of a small city flash frozen and then explosively vaporized over the course of a few weeks. The resulting cloud of ice crystals, dust, grains, and gas molecules would form a structure visible across millions of kilometers. From Earth, even at a distance of hundreds of millions of kilometers, such a cloud would appear as an extended glowing envelope around the comet. Telescopes would see a massive coma, the fuzzy atmosphere surrounding the nucleus, and long sweeping tails pointing away from the sun. The brightness would increase dramatically. Not just a little, we're talking about orders of magnitude. The object would go from barely visible to naked eye visibility, maybe even becoming one of the brightest objects in the night sky for a period of weeks. Spectroscopy would reveal a rich emission spectrum, Freshly exposed volatiles would fluoresce in dozens of wavelengths as solar ultraviolet radiation excites molecules and causes them to glow. You'd see strong lines from water, carbon dioxide, carbon monoxide, hydroxyl radicals, cyanide, sodium, all the standard cometary molecules in abundance. Polarimetry would detect changes as the newly ejected particles scatter sunlight. The polarization signature would evolve as the coma expands and particles of different sizes become dominant at different distances from the nucleus. Infrared observations would detect thermal emission from warm dust grains. As the sun heats the ejected material, it radiates in infrared wavelengths. Instruments like the James Webb Space Telescope's infrared cameras would see a glowing halo that persists even after the object moves away from perihelion. And if fragments broke off, if the violence of the outgassing fractured the nucleus, we'd see multiple bright points within the coma. Secondary sources of activity, each piece contributing to the overall debris field. This is what happens when a comet loses a significant fraction of its mass. We've seen it before. We know what to look for. The signatures are unmistakable. So where are they? Current observations as of early November 2025 show that 3I Atlas is active. There is a coma, there are jets. Spectroscopy detects carbon dioxide and other volatiles. The brightness has increased, but the scale is all wrong. The coma is present but modest. Not the massive extended structure you'd expect from billions of tons of mass loss. The jets are visible in high-resolution images, but not the dramatic sustained features associated with extreme outgassing. The brightness has increased, yes, but by factors of a few, not factors of tens or hundreds. The spectroscopic line strengths are elevated but not off the charts. The tail, while present, is not a sweeping streamer, millions of kilometers long. It's more like the tail of a moderately active comet, visible, measurable, but not spectacular. In short, everything suggests an active comet behaving within normal parameters. Not a comet in the throes of losing 10% of its mass in a catastrophic venting event. Could the debris be hidden? Let's explore that possibility carefully because it's the most conservative explanation. It requires no new physics. Just unfortunate circumstances, viewing geometry. Maybe we're looking at the debris cloud edge-on, seeing it through its narrowest dimension, or maybe the ejected material is concentrated in jets pointing toward or away from us, so we're not seeing the broad face of the cloud. This is plausible for a brief period, but 3I Atlas has been observed from multiple angles over several months. As it moves through space and Earth orbits the Sun, the viewing geometry changes. If there's a massive debris cloud, we should have seen it from at least some viewing angles by now. By
dark material. Maybe the ejected material is primarily gas with very little dust. Gas doesn't scatter sunlight efficiently, so a gas-dominated coma would be fainter than a dust-rich one. This fits with the carbon dioxide-rich composition. CO2 sublimates cleanly without producing much dust, so perhaps 3I Atlas is ejecting enormous amounts of gas that's simply too faint to detect in reflected sunlight. But gas produces emission lines, it fluoresces. Spectroscopy should reveal intense emission features if billions of tons of gas are present. And while the spectroscopy does show activity, it doesn't show the extreme line strengths you'd expect for such massive gas production. Timing. Maybe the mass loss happened in a brief burst and the debris cloud is still expanding. It hasn't reached the size or density where it becomes easily visible. Give it more time and the evidence will appear. This is the wait-and-see explanation. And it's why the November-December 2025 observation window is so critical. If the debris cloud is there, but just becoming visible now, the upcoming observations will detect it. Small particles. Maybe the ejected material consists of particles much smaller than typical comet dust. Particles smaller than the wavelength of visible light scatter differently, less efficiently in some cases. They might be harder to detect in standard photometry. But polarimetry is sensitive to particle size.
and the polarimetric observations already show unusual signatures. If the particles are extremely small, that should be apparent in the data. Moreover, very small particles are quickly swept away by radiation pressure, creating extended structures that should be observable. Each of these explanations has merit. Each could account for why we're not seeing what we expect if considered in isolation. But together, requiring the viewing geometry to be unfavorable and the material to be unusually dark and the timing to be inconvenient and the particles to be atypical, that's a lot of special circumstances all happening at once. Occam's razor suggests we should favor simpler explanations. And the simplest explanation, uncomfortable as it may be, is that the massive debris cloud doesn't exist because the massive mass loss didn't happen. Which brings us back to the question, if the object accelerated without ejecting the expected mass, what force caused the acceleration? Science progresses by proposing hypotheses and testing them. When faced with an anomaly like the 10th anomaly of 3I Atlas, we need to lay out all possible explanations, assign them rough probabilities based on current evidence, and determine what observations would confirm or refute each one. Let's walk through 4 hypotheses ranging from most conservative to most speculative. Hypothesis 1. 60% weight, natural comet, hidden debris. The claim, 3I Atlas is a natural comet. The debris cloud exists. We simply haven't detected it yet due to observational limitations. Why it's plausible. This explanation requires no new physics, no exotic mechanisms, no paradigm shifts. It says we're dealing with an unusual but fundamentally normal object, and patience, plus better data, will resolve the mystery.
The debris could be rendered invisible or difficult to detect by viewing geometry that places the densest parts of the cloud out of our line of sight. A gas-dominated composition with minimal dust production, particle sizes that scatter light inefficiently in the wavelengths we're observing, timing where the cloud hasn't fully expanded or hasn't moved into optimal viewing positions. Yet, what would confirm it? The November-December 2025 observations detect a large luminous debris cloud. Spectroscopy reveals intense emission lines consistent with billions of tons of gas. Infrared imaging shows thermal emission from dust. The brightness increases to levels commensurate with massive mass loss. If this happens, the mystery is solved. 3I Atlas becomes a benchmark for extreme interstellar comets, objects that behave more violently than typical solar system comets due to their unusual compositions and long exposure to interstellar conditions. Papers are published, models are updated.
Science moves on. Why it's not certain. We've had months to observe from multiple angles. The spectroscopy, while showing activity, doesn't show the extreme emission strengths expected. The photometry doesn't match. As time passes, this hypothesis becomes less likely, but it's still the most conservative and therefore assigned the highest weight. Hypothesis 2, 25% weight, exotic natural mechanism. The claim. The acceleration is real, but the mass loss is far more efficient than our models predict. Some unusual physical or chemical process allows the object to generate thrust with much less visible debris than expected. Why it's plausible. Our models of cometary outgassing are based on solar system comets, objects formed in our own protoplanetary disk. An interstellar comet formed in a completely different chemical environment might behave in ways our models don't capture.
Possible mechanisms include ultravolatile ices, materials like hydrogen ice or helium ice that sublimate at extremely low temperatures and produce jets moving at very high velocities. Higher ejection speeds mean less mass is needed for the same thrust. These ices would be nearly invisible. They don't produce dust, and their spectroscopic signatures are hard to detect. Highly collimated jets. If the outgassing is concentrated in very narrow, precisely directed jets rather than diffuse emission.
the efficiency of thrust per unit mass increases dramatically. You could get the observed acceleration with far less total mass loss. Surface properties. Perhaps the nucleus has an unusual crust or surface structure that channels outgassing in specific ways. Porous, honeycomb-like structures could create preferential flow paths that maximize thrust efficiency. Chemical reactions, exotic chemistry involving carbon dioxide, carbon monoxide, and other species might produce reactive jets that accelerate particles to higher speeds than thermal sublimation alone would achieve. What would confirm? Its spectroscopy detects signatures of ultra-volatile species. High-resolution imaging reveals highly collimated jets with unusual morphology. Models incorporating extreme chemistry or novel surface physics successfully reproduce the observed acceleration with minimal visible debris. This hypothesis stretches our understanding but doesn't break it. It says the universe has more diversity than we've accounted for, and 3I Atlas is teaching us about formation environments we've never directly studied. Why it's uncertain. Ultravolatiles, like hydrogen ice, are extraordinarily difficult to retain over interstellar timescales. Even in the cold of space, cosmic rays and stellar radiation would boil them away over millions of years.
And highly collimated jets should still produce some visible structure, something we're not clearly seeing. Hypothesis 3, 10% weight measurement error. The claim, the 4 arcsecond positional offset, is an artifact. The acceleration isn't real. We're measuring something incorrectly or misinterpreting the data. Why it's plausible science is hard. Mistakes happen. Instrumental systematics calibration errors, unaccounted for perturbations. These can all produce false signals that look real until someone finds the bug. Possible sources of error include gravitational lensing, miscalculation. Maybe the sun's gravitational bending of light is larger than predicted, or there's some additional lensing from structure in the solar corona that we're not accounting for properly. Reference frame issues. Astrometry requires precise knowledge of the positions of background stars used as reference points. If those positions are slightly wrong, the derived position of 3I Atlas could be offset.
Systematic instrumental effects. ALMA is an interferometer. It combines signals from multiple dishes. If there's a systematic error in how those signals are phased or calibrated, it could introduce positional offsets, parallax or timing errors. Slight errors in the timing of observations or in accounting for Earth's motion could translate into apparent positional shifts. What would confirm? An independent team reanalyzes the data and finds an error, or different instruments using completely different techniques fail to reproduce the offset, or someone identifies a specific systematic that perfectly explains the discrepancy. If this happens, it's embarrassing for the original team, but ultimately healthy for science. Errors are corrected. The community learns. 3I Atlas becomes a cautionary tale about the importance of cross-checks and skepticism. Why it's unlikely. The measurements have been checked and rechecked.
Multiple independent observatories have confirmed the positional anomaly. ALMA is a professional-grade facility with rigorous calibration procedures. While mistakes are always possible, the level of error required to produce a false 4 arcsecond offset is substantial. It's not a subtle bug, it's a glaring systematic. Those usually get caught early. Hypothesis 4, 5% weight, unknown, mechanism. The claim, the object accelerated without ejecting the expected mass. It's using some mechanism we don't understand, natural or otherwise. This is speculation, but it's speculation invited by the data. When you eliminate natural explanations and measurement error, what remains might be improbable, but it demands consideration.
Possible mechanisms include natural but novel radiation pressure on an unusual structure, If the nucleus has a very low density or an extremely high surface area, perhaps a highly porous fractal structure, solar radiation pressure could produce measurable acceleration. This requires the object to be much lighter or larger than we think. Plasma interactions. The solar wind is a stream of charged particles. If 3I Atlas has a magnetic field or is shedding ionized gas in large quantities, electromagnetic forces might contribute to the acceleration. This seems unlikely given the observed plasma environment, but plasma physics can be counterintuitive. Some exotic effect. Perhaps there's a physical mechanism involving the intense magnetic fields near the sun or the warped spacetime in the solar gravitational well that we haven't discovered yet. New physics is rare but not impossible. Artificial propulsion system. If 3I Atlas were a probe, a spacecraft, it might use the perihelion pass to adjust its trajectory. A controlled burn using stored propellant like carbon dioxide ice or a solar sail deployed near the sun could produce the observed acceleration without the mess of random outgassing. The artificial hypothesis explains many features. The trajectory optimized for planetary encounters, the composition engineered materials rather than natural formation, the timing maneuver. During conjunction to avoid Earth-based observation, the lack of debris, controlled thrust, not chaotic venting, the blue color, propellant fluorescence, the anti-tail, deliberate jet orientation. But here's the critical point: explaining observations doesn't make a hypothesis true. We need independent evidence, positive detection of artificial structures, materials, or signals. Not just it fits, but it can't be natural. What would confirm it: detection of clearly artificial features, regular patterns in brightness or emissions that suggest communication or control, spectroscopic signatures of industrial materials, radio signals, repeated course corrections that can't be explained by outgassing, discovery of other similar objects with the same anomalous properties, suggesting a population of probes rather than one-off natural rarity. Why it's low probability. Extraordinary claims require extraordinary evidence. The vast majority of astronomical anomalies have turned out to be natural. Pulsars weren't LGM little green men. Fast radio bursts aren't alien beacons. The history of science teaches humility. The universe is weird, but it's not usually artificial. Moreover, interstellar travel is hard. The energy requirements are staggering. The timescales are long. Why would anyone send a slow-moving probe on a journey that takes tens of thousands of years? These are valid objections.
They're why this hypothesis sits at 5%, but 5% is not zero. And if the December observations rule out hypotheses 1, 2, and 3, then we're left staring at something profoundly uncomfortable.
Let me be very clear at the outset. This is speculation. The artificial origin hypothesis for 3I Atlas is not proven, not confirmed, not the scientific consensus. It's one possibility among several assigned low probability based on current evidence. But it's a possibility that deserves serious consideration, not because it's likely, but because the implications are so profound that even a small chance demands investigation. If you were an advanced civilization looking to explore the galaxy, how would you do it? Crewed missions are impractical. The distances are too vast, the timescales too long. Even traveling at 10% of light speed, enormously fast by our standards, reaching the nearest star would take decades, and we're nowhere close to achieving such speeds. But probes, small automated spacecraft designed to travel slowly, gather data, and perhaps report back using methods we can't yet imagine. That's feasible. In fact, we're already planning such missions. Projects like Breakthrough Starshot aim to send tiny probes to Alpha Centauri using laser-push sails. The technology is within reach. Now imagine a civilization a million years ahead of us. What could they do? They might seed the galaxy with probes, sending them out in vast numbers over immense timescales. Most would travel through empty space, gathering data on the interstellar medium magnetic fields, cosmic rays, but a few would encounter star systems, our Sun, for instance. How would such a probe behave? It would approach the star for several reasons. Stars are interesting. They're sources of energy. They're gravitational anchors around which planets form. If you're studying a stellar system, you want to get close. You'd aim for the ecliptic plane because that's where planets orbit. That's where the action is. You'd design your trajectory to maximize close encounters with interesting worlds, Mars, Venus, Jupiter. You'd use gravity assists to adjust your path, conserving fuel. You'd probably perform some maneuver near perihelion. The intense solar environment provides opportunities. You could deploy a solar sail and gain velocity. You could vent stored propellant heated by the sun, using it as a crude thruster. You could adjust your trajectory to target the next object of interest. And if you were clever, you'd time that maneuver during solar conjunction when Earth-based civilizations, if they exist, can't easily observe you. Not because you're hiding necessarily, but because it's the natural time to act. The geometry is optimal. The sun is close. The gravitational potential is deep. An Oberth maneuver at perihelion is one of the most efficient ways to change velocity in a gravitational field. Now think about the composition such a probe might have. You wouldn't build it out of water ice. Water is reactive. It freezes and expands, cracking structures. It's not stable over millions of years of interstellar travel. You'd use materials that withstand temperature swings and radiation. Carbon dioxide ice is actually a decent choice for propellant. It's stable at low temperatures, sublimits. Cleanly, when heated, doesn't leave corrosive residue. Many spacecraft use similar volatiles for attitude control. Nickel alloys are standard in aerospace engineering. Strong, heat-resistant, relatively lightweight. If you're building something to survive close approaches to stars, nickel-based materials make sense. So a probe designed for interstellar travel and stellar flybys might naturally have low water content. High carbon dioxide content, unusual metal ratios, composition optimized for engineering rather than natural formation. Its behavior would also differ from a natural comet. Jets wouldn't follow solar heating patterns. They'd be controlled, directed, optimized for thrust. Brightness changes would correlate with system activation rather than random outgassing. The color might reflect propellant chemistry. Carbon dioxide fluorescence produces blue light. Acceleration wouldn't match debris production, because thrust is deliberate, not chaotic. Every anomaly we've discussed, all 9, plus the 10th, fits comfortably into this framework, but does fitting equal truth? Absolutely not. I can construct a narrative that explains anything if I'm creative enough. The test of a hypothesis isn't whether it explains observations. The test is whether it makes testable predictions and whether alternative explanations are definitively ruled out. So what would we need to confirm? Artificial origin first. Exhaust all natural explanations. Show that no combination of exotic chemistry, unusual physics, or edge case conditions can reproduce the behavior. This is extraordinarily difficult. Nature is versatile. There's always one more rare scenario to consider. Second, positive evidence of design. Not just, this is weird, but this can't be natural. Patterns that are too regular. Structures that show engineering principles. Spectroscopic signatures of manufactured materials, industrial polymers, refined metals, isotopic ratios that don't occur in nature, modulation in brightness or emissions that looks like communication or control systems cycling. What would manufactured materials look like in a spectrum? Imagine detecting emissions from synthetic polymers, long-chain organic molecules with repeating structures that wouldn't form naturally, or finding isotopic ratios that are impossible without deliberate enrichment like uranium. 235, concentrated to levels seen only in nuclear fuel or deuterium ratios that suggest chemical processing rather than natural fractionation. Spectroscopy can reveal not just what elements are present, but how they're arranged. Natural minerals have characteristic crystal structures that produce specific spectral features. Artificial materials, ceramics, alloys, composites often have different structures, different thermal properties, different ways of absorbing and emitting light. An expert spectroscopist, given high-quality data, might be able to distinguish between naturally occurring minerals and their manufactured equivalents. Or consider geometric patterns. Natural objects tumble chaotically, their rotation rates governed by whatever torque gravitational interactions or past collisions imparted. But a spacecraft maintains attitude control. It might spin at a precise constant rate for stability, or it might orient itself deliberately, pointing specific faces toward the sun or toward targets of interest. If 3I Atlas's brightness variations are perfectly periodic, oscillating with a period that remains constant to within fractions of a second over weeks of observation, that's suspicious. Natural objects subjected to outgassing experience torques that change their rotation rates. A perfectly stable spin suggests either incredible luck or deliberate control. Even more suspicious would be brightness variations that aren't consistent with a tumbling object at all. If the object sometimes dims, sometimes brightens in patterns that don't match any rotation model, as if surfaces are being actively oriented rather than passively illuminated, that would be very hard to explain naturally. Or imagine detecting modulated signals. Not a steady glow, but a brightness that pulses or varies in a structured way. If that variation carried information, a binary pattern, a mathematical sequence, anything non-random, it would be virtually impossible to explain as natural. We're not seeing any of this. Not yet. The spectroscopy shows molecules we'd expect from ices. The brightness variations, while unusual, aren't perfectly periodic or clearly modulated. There's no smoking gun. But we're still looking. Every new observation is an opportunity to detect something definitive, and the threshold for definitive is high, as it should be. Extraordinary claims require extraordinary evidence. A strange spectrum isn't enough. An odd rotation isn't enough. We need something that can't be explained any other way, something that forces even the most skeptical observer to admit that natural processes can't account for it. Third, independent confirmation. 1 anomalous object is a curiosity. 2, with similar properties, is a pattern. 3 is a phenomenon. If 3I Atlas is artificial, it's probably not alone. There should be others. Maybe we've already seen them and didn't recognize them. Maybe the next interstellar visitor will show the same features. Fourth, rule out human error and bias. We're pattern-seeking creatures. We see faces in clouds and hear voices in static. We need to be ruthlessly skeptical of our own tendency to see intention where there's only randomness. None of these criteria are met yet. We have one object. We have anomalies that might have natural explanations. We have no smoking gun.
But we also have an observation campaign underway right now in November and December 2025 that will dramatically narrow the possibilities. Let me address the counterarguments because they're important, and they're why most scientists remain skeptical. Objection 1. Astronomical anomalies have always turned out to be natural. True, pulsars, quasars, gamma-ray bursts, fast, radio bursts, all initially mysterious, all ultimately explained by natural astrophysics. The track record says when you see something weird in the sky, bet on nature, not aliens. This is a powerful prior. It says we should exhaust every possible natural explanation before invoking intelligence. And that's exactly what the scientific process is doing. The artificial hypothesis sits at low probability precisely because of this historical pattern. But history also shows we're bad at predicting what's possible. Every generation of astronomers thinks they understand the universe, and every generation is surprised by the next discovery. So while the prior is strong, it's not absolute. Objection 2. Interstellar travel is too hard. At our current level of technology, yes. But we're discussing civilizations that might be millions or billions of years ahead of us.
The gap between us and them would be larger than the gap between us and bacteria. We can't imagine their capabilities any more than a bacterium could imagine the internet. They might have propulsion systems based on physics we haven't discovered. They might have solved the energy problem in ways we can't conceive. Moreover, travel doesn't have to be fast. A probe traveling at 1% of light speed would take 400 years to cross the distance to the nearest star, long by human standards, but trivial on cosmic timescales. A civilization thinking in terms of millions of years could afford patience. Objection 3. We should have seen more. If probes are common, if they're cruising through the galaxy in large numbers, why have we only detected 3 interstellar objects, and why is only one of them clearly anomalous? First, we've only been looking seriously for a few decades. Our detection capabilities have improved dramatically just in the last few years. Surveys like Atlas, Rubin Observatory, and others are just coming online. We might be detecting objects now that we would have missed entirely a decade ago. Second, most probes would pass through unnoticed. Only those that come relatively close to Earth and Sun would be detected. The true population could be far larger than the few we've spotted. Third, if probes are designed to be inconspicuous to blend in with natural objects, we might have seen many and classified them as asteroids or comets without recognizing their true nature. It's an argument from absence. We don't see what we expect. Therefore, it doesn't exist. But absence of evidence isn't evidence of absence, especially when our search capabilities are still developing. So where does this leave the artificial hypothesis? It remains speculative, low probability, assigned 5% weight, not because it's likely, but because it's non-zero and the implications are enormous. If December observations show no debris cloud, if the acceleration persists without explanation, that probability will rise. Not to certainty, but to a level where serious investigation is warranted.
The scientific community would need to request more observations with every available instrument. Look for additional interstellar visitors with similar properties. Search for signals or patterns we might have missed. Consider missions to intercept or study the object up close. Expand SETI efforts to include anomaly detection in small body behavior. Because if we're wrong, if we dismiss the possibility out of hand, and it turns out that evidence of extraterrestrial intelligence just passed through our solar system while we shrugged it off as a weird comet, that would be the greatest missed opportunity in human history.
3IO Atlas isn't happening in isolation. The year 2025 has been remarkable for astronomical discoveries, several of which echo the themes of unexpected composition and behavior that challenge our models. Let's zoom out and look at the broader landscape. Discovery 1. The carbon dioxide exoplanet. In September 2025, a team using the James Webb Space Telescope announced the characterization of an exoplanet atmosphere that defies expectations. The planet, designated WASP 243b, orbits a sun-like star about 400 light-years away. It's a hot Jupiter, a gas giant, orbiting close to its star, tidally locked with one side permanently facing the heat. Standard models predict these atmospheres should be dominated by hydrogen and helium with traces of water vapor, carbon monoxide, perhaps some methane. WASP 243b's atmosphere is nearly 50% carbon dioxide. The water content is negligible. Hydrogen and helium are present but not dominant. It's the atmospheric equivalent of 3I Atlas's composition, carbon-rich water poor, completely backwards from what theory predicts. The discovery team published in Nature. The reaction in the exoplanet community was a mix of excitement and confusion. Nobody has a good explanation for how you get an atmosphere like this. The leading hypothesis is that the planet formed far from its star in a carbon-rich region and then migrated inward. But that doesn't fully explain the extreme ratio. What's the connection to 3I Atlas? On the surface, none. One is an interstellar comet in our solar system. The other is an exoplanet atmosphere hundreds of light-years away. But thematically, they're deeply connected. Both are examples of the universe producing something that doesn't fit our models. Both challenge assumptions about composition and formation. Both force us to confront the uncomfortable possibility that our theories built on observations of our own solar system might not be as universal as we thought. For decades, we've been building models of planetary formation based on what we see here. We assumed our solar system was typical, that other systems would look similar with some variation. But the more exoplanets we discover, the more we realize how atypical our solar system might be. Hot Jupiters shouldn't exist according to early models. They can't form where they're observed. Super-Earths in tight orbits shouldn't exist. Ice giants with retrograde orbits shouldn't exist. And now, atmospheres dominated by carbon dioxide shouldn't exist. Yet they all do. The lesson is humility. The universe is under no obligation to conform to our expectations. Formation processes are complex. Environments are diverse. And edge cases once thought rare turn out to be common when you have billions of star systems to sample from. So, when we look at 3I Atlas and its carbon dioxide-rich composition and scratch our heads, maybe we shouldn't be surprised. Maybe objects like this are common in certain stellar environments, the same environments that produce carbon-rich exoplanet atmospheres. Maybe the fact that we're finding both an odd interstellar object and an odd exoplanet atmosphere in the same year isn't coincidence but signal. A signal that says the cosmos has more tricks than we've cataloged, more diversity than we've modeled, more strangeness than we're prepared for. This doesn't mean 3I Atlas is natural. It doesn't prove anything one way or the other, but it provides context. It reminds us that weirdness is becoming the norm in astronomy. Discovery 2: Gravitational Lensing. Precision Tests. In March 2025, a collaboration of physicists published results from an ultra-precise gravitational lensing experiment. Using a network of telescopes positioned across Earth, they measured the deflection of starlight passing near the Sun during a partial eclipse. This is the same experiment that confirmed Einstein's general relativity in 1980s. But with modern instruments and analysis techniques, the precision is thousands of times better. The result, general relativity, holds to within 1 part in 10 million. The measured deflection matches Einstein's prediction perfectly. No deviations, no anomalies, no hints of modified gravity or extra dimensions, or any of the alternatives theorists have proposed. The universe, at least in this corner and under these conditions, follows the rules. Space-time bends exactly as predicted. Gravity works the way it should. Why does this matter for 3I Atlas? Because one possible explanation for the positional offset was gravitational lensing. Maybe the Sun's warping of space-time shifts the apparent position of 3I Atlas more than standard calculations suggest. But the March 2025 lensing experiments rule that out. General relativity works. The lensing formula is correct. The predicted deflection for 3I Atlas's geometry is about 0.27 arcseconds, far too small to explain the observed 4 arcsecond offset, which means the offset is real. It's not a relativistic effect. It's not space-time curvature playing tricks on us. Something is physically pushing the object off course. This narrows the field. It eliminates one hypothesis and strengthens the case that non-gravitational acceleration is real. Discovery 3: AI-driven anomaly detection. In June 2025, the European Space Agency deployed an artificial intelligence system called Sentinel AI to monitor small solar system bodies. The system uses machine learning trained on decades of asteroid and comet observations. When a survey telescope detects a new object, Sentinel AI analyzes its orbit brightness spectrum morphology. It compares those properties to known populations. And if something doesn't fit, if the object shows characteristics that are unusual, the system flags it for human review and triggers automatic follow-up observations. In its first 3 months, Sentinel AI identified 17 objects with anomalous properties. Most turned out to be misclassifications or instrumental artifacts. But 2 were genuine discoveries: a main belt comet with unusually high carbon monoxide production, and a near-Earth asteroid with a rotation period so fast it should be shedding material but somehow isn't. The broader point we're entering, an era where anomaly detection is automated. Machines are spotting the weird stuff. And machines don't have biases. They don't assume things should look a certain way. They just compare data to models and flag mismatches. 3i Atlas was discovered by a traditional survey, but many of its anomalies were flagged by automated systems. The unusual orbit was noted immediately because software calculated the trajectory and recognized it as hyperbolic. The compositional oddities were flagged when spectroscopic pipelines compared data to templates and found huge residuals. This is the future. Large surveys like Rubin Observatory will detect millions of objects. Humans can't analyze them all. We need AI to sift through data, identify outliers, prioritize follow-up. And as those systems improve, we're going to find more objects like 3i Atlas, maybe many more. The detection rate for interstellar objects is currently about 1 every 3 years. But that's limited by our sensitivity. As telescopes get better and algorithms get smarter, we'll find fainter objects, more distant objects, objects on less favorable orbits. The true population of interstellar visitors passing through the solar system at any given time could be hundreds or thousands. We're just now developing the ability to see them. If even a small fraction show anomalies like 3i Atlas, if even 1% turn out to behave in ways natural physics struggles to explain, then we're living through a paradigm shift. We're transitioning from a universe where interstellar objects are rare curiosities to a universe where they're common enough to study systematically. And in that universe, the question, are we alone, becomes answerable not through radio signals or megastructures, but through the behavior of small bodies drifting through our neighborhood. Let's step back from the technical details and ask, why should anyone care? Why does it matter whether a chunk of ice and rock from another star system is moving slightly off course? Why should the public, the media, policymakers, anyone beyond a small community of astronomers pay attention to 3i Atlas? Because the answer to the 10th anomaly determines what we think is possible. For science, if the follow-up observations in November and December 2025 show a massive debris cloud, if we detect the billions of tons of ejected material, then here's what we learn. Interstellar objects can be far more extreme than we thought. Comets from other star systems aren't just variations on a theme. They're entirely new categories, objects with compositions reflecting alien chemistries, behaving in ways our solar system never prepared us for. This is still a huge deal. It expands the boundaries of planetary science.
It tells us that the diversity of environments in the galaxy is greater than our models capture. Every new interstellar visitor is a free sample from another stellar system, a piece of data delivered to our doorstep. We don't have to send probes across light years. The universe sends objects to us. But if the observations don't show the debris cloud, if the acceleration remains unexplained by visible mass loss, then we're in different territory entirely. Then we have to ask, is there some mechanism of propulsion we don't understand? Some way for natural objects to gain velocity without shedding commensurate mass? Some interaction between the comet and the solar environment that produces thrust in ways we've never seen? Or are we looking at something that's not entirely natural? Either answer revolutionizes a field.
Either we discover new physics, new mechanisms by which objects can move through space, or we discover we're not alone, and evidence of intelligence just passed through our solar system. The implications for physics and astronomy are staggering. If momentum conservation applies differently than we thought, if there are loopholes or exotic regimes where the rules bend, that reshapes everything from spacecraft design to our understanding of how galaxies evolve. If artificial objects are detectable via subtle anomalies in their motion, that opens an entirely new avenue for SETI, the search for extraterrestrial intelligence. We've been listening for radio signals for decades. Maybe we should also be watching for objects that move wrong. For planetary defense, right now we track asteroids and comets that might threaten Earth using gravitational models. We measure an object's position and velocity, calculate its orbit, and predict where it will be years or decades in advance. This works remarkably well as long as objects move predictably under gravity alone. But if objects can accelerate unpredictably, if non-gravitational forces are significant and hard to model, then our predictions have uncertainty. Our tracking systems have blind spots. That's not a reason to panic. The vast majority of objects in the solar system are inert rocks following Newton's laws precisely. And 3I Atlas isn't a threat, it's not coming anywhere near Earth, but it's a reminder that our models are only as good as our understanding. If there are mechanisms, natural or otherwise, that allow objects to change course without warning, then we need better contingency plans. We need to account for uncertainty. We need to monitor objects continuously, not just calculate orbits once and assume they're fixed. Planetary defense depends on prediction. Anything that makes prediction harder is a concern. Not an immediate threat, but a gap in our defenses that needs addressing. For philosophy and meaning. For most of human history, we've assumed we're special. Not because we're better or smarter, but simply because we're here and conscious, and as far as we can tell, nobody else is paying attention. The silence of the cosmos has been deafening. We've sent signals, we've listened for replies, we've scanned thousands of stars for signs of technology, and we've found nothing. The universe seems empty, dead, indifferent. But what if it's not empty? What if the silence is just a matter of not knowing what to listen for? What if techno-signatures don't look like radio signals or Dyson spheres, but like objects moving through space in ways natural physics can't quite explain? What if someone out there is exploring the galaxy the same way we're planning to sending probes, gathering data, mapping the neighborhood, and 3I Atlas is one of those probes? This is not idle speculation. This is a hypothesis some scientists are taking seriously. Not because they want to believe in aliens, not because they've given up on natural explanations, but because the data is pointing in a direction that can't be ignored. If we're not alone, if there are other intelligences out there, other civilizations that have solved the problem of interstellar travel and are actively exploring, then the entire human story changes. We're no longer the main characters. We're bit players in a much larger drama. The universe isn't a stage built for us. It's a stage we happen to occupy along with countless others. That's either terrifying or exhilarating, depending on your personality. Terrifying because it means we're not special. Our struggles, our achievements, our entire history might be a footnote in a cosmic narrative we can barely perceive. Exhilarating because it means we're not alone. The vast darkness between stars isn't empty after all. There's company out there, minds that think, explore, question, just like we do. For people who spend their lives wondering whether life and intelligence are rare or common, whether the universe is silent or teeming. 3I Atlas is one of the most significant objects ever observed. If it's natural, it teaches us about diversity and the limits of our models. If it's something else, it answers the oldest question humanity has ever asked. Are we alone for the future? We're living through a moment of potential paradigm shift, the kind of moment that happens maybe once or twice in a generation, where an observation or discovery forces a field to reconsider its foundations. December 19th, 2025, the date of 3I Atlas's closest approach to Earth, will bring answers, or at least will narrow the possibilities. If massive debris appears, the mystery resolves into a natural explanation. Papers are published, models are refined, life goes on. If no debris appears, the mystery deepens. More observations are requested, more hypotheses are proposed. The debate intensifies. And somewhere in that debate, we might stumble into new physics, new understanding, or however unlikely confirmation that we're not alone. Either way, the field advances. Knowledge expands. we learn something fundamental about the universe and our place in it. That's why this matters. That's why 3i Atlas deserves attention. Not because it's definitely aliens, not because it's definitely going to revolutionize physics, but because it might. And might is enough. The clock is ticking. November and December 2025 represent the optimal observation window. On December 19th specifically, 3i Atlas makes its closest approach to Earth, roughly 170 million miles, or about 270 million kilometers. That's still a vast distance farther than the Sun, but close enough for detailed study. The viewing geometry will be favorable. The object will be in the constellation Pisces, well placed for observation from both northern and southern hemispheres. It won't be hidden behind the Sun or lost in the glare of the Milky Way. It'll be accessible to every major telescope on Earth and in space. Dozens of observatories have requested or been allocated time to observe 3i Atlas during this window. The James Webb Space Telescope has dedicated observing slots. Hubble is scheduled for follow-up imaging. ALMA will continue high-precision astrometry. Ground-based observatories with adaptive optics, Keck VLT Gemini will all be watching. This is the moment. The cosmic equivalent of holding your breath before opening an envelope that might contain life-changing news. What the telescopes are looking for. Extended morphology. Does the object have a large, luminous tail? A coma that's grown significantly since perihelion. Any structure jets streamers fragments that suggests massive material ejection. Imaging in optical and infrared wavelengths will capture the overall shape and extent of any debris. If there's a massive cloud, it'll show up as a diffuse glow extending far beyond the nucleus. Morphology will tell us whether outgassing was uniform or concentrated in specific regions, whether the object is intact or fragmenting. Photometry. Has the brightness changed in ways consistent with millions or billions of tons of mass loss? Phototrick monitoring measures the total amount of light coming from the object as a function of time. If massive outgassing occurred near perihelion, we'd expect the brightness to have spiked and then gradually declined as the debris cloud expands and thins. Specific patterns in the light curve oscillations, periodic variations could indicate rotation or active regions turning on and off. Spectroscopy. What molecules are present in the coma and in what quantities? Spectroscopy splits light into its component wavelengths, revealing the chemical fingerprint of the gas surrounding the nucleus. If billions of tons of material were ejected, we'd expect intense emission lines from water, carbon dioxide, carbon monoxide, cyanide, and other volatiles. The strength of these lines is directly proportional to the amount of gas present. Weak lines mean little gas, strong lines mean a lot. By comparing the observed line strengths to models, we can estimate the total mass of the coma and determine whether it matches the amount needed to explain the acceleration. Astrometry. Where exactly is the object now and does its position match predictions? Continued astrometric measurements will track whether the non-gravitational acceleration persists. If the object is now back on a purely gravitational trajectory, that suggests the acceleration was a temporary event tied to perihelion. If the deviation continues, that's more troubling. It implies an ongoing force. Precise position measurements also allow us to refine models of what happened near perihelion, potentially distinguishing between different outgassing scenarios or identifying patterns in the acceleration that provide clues to the mechanism. Radio observations. Is there any emission at radio wavelengths? Natural comets don't produce strong radio signals, but certain plasma interactions or magnetic fields could. Artificial objects might emit radio noise from electronics or power systems, a long shot but worth checking. ALMA and the Very Large Array will be listening. If there's anything to hear, they'll detect it. Polarimetry. How has the polarization signature evolved? Polarimetry is exquisitely sensitive to particle size, shape, and composition. Changes in the polarization signal would indicate that new material has been exposed or that the coma particles are evolving, perhaps growing as ices condense onto grains, or fragmenting as thermal stress cracks them. The unusual negative polarization observed earlier is a unique fingerprint. If it persists, that tells us the particles remain anomalous. If it changes, that provides clues about what's happening in the coma. 3 possible outcomes. The scientific community has been running through scenarios trying to anticipate what the December observations might reveal. Scenario A: massive debris detected. The images come back showing an extended luminous cloud. The spectrum shows intense emission lines. The photometry indicates a brightness spike consistent with huge mass loss. The infrared observations detect thermal emission from warm dust spreading through space. In short, the debris is there. We just hadn't seen it yet. This is the conservative outcome. It's what most astronomers expect or hope for because it requires no paradigm shift. 3I Atlas is an extreme comet, the most active interstellar comet ever observed, but still a comet. Natural, explicable within the bounds of known physics. Papers are published detailing the unprecedented outgassing event. Models are updated to accommodate interstellar objects with exotic compositions and behaviors. 3I Atlas becomes a benchmark and a cautionary tale about making assumptions, a reminder that the universe is stranger than our parochial solar system prepared us for. The 10th anomaly is resolved. Science moves on. Scenario B: no debris, persistent acceleration. The images show modest activity, no massive cloud. The spectrum shows elevated emission, but nothing extraordinary. The photometry is inconsistent with billions of tons of mass loss. The astrometry reveals continued deviations from a purely gravitational trajectory. This is the uncomfortable outcome. It forces us to confront the possibility that something fundamental is different about this object. Maybe it's still natural, some exotic mechanism we don't understand yet. Ultra-volatile ices venting invisibly. Plasma interactions we haven't modeled correctly. Some edge case of physics that only manifests under specific conditions near a star. Or maybe it's not entirely natural. Maybe the artificial hypothesis moves from fringe speculation to serious consideration. Either way, the debate intensifies. More observations are requested. Proposals for missions to intercept and study the object up close are drafted. SETI researchers start paying attention, looking for patterns or signals we might have missed. The story makes headlines, and the community wrestles with the possibility that 3I Atlas is one of the most significant discoveries in astronomy. Scenario C: ambiguous data. Maybe we see some mass loss, but not enough. Maybe the photometry shows brightness changes that are hard to interpret. Maybe the spectroscopy reveals unusual molecules that don't fit standard comet models. This is the messy, unsatisfying outcome, but probably the most realistic. Because nature is complicated. Data is noisy. Measurements have uncertainties. Clean, definitive answers are rare. If we land in scenario C, the debate continues. Some scientists argue the debris is there, but we're still not seeing it properly. Others point to the inconsistencies and suggest we need new physics. A smaller group whispers about artificial origins. More data is needed, more time, more observations. 3I Atlas becomes a long-term project, not a quick mystery solved. The truth is, by the time you're hearing this, some of those observations may already be complete. Data might be sitting on hard drives waiting for analysis. Preliminary results might be circulating in private emails among collaborators. The answer might already exist, we just don't know it yet. That's the strange temporal dislocation of making content about current events. I'm recording this in early November 2025. You might be listening in December or January 2026 or years later. By the time these words reach your ears, the story might have moved forward. Conclusions might have been drawn, or the mystery might have deepened. Let's think through the consequences of each scenario more carefully, because how this resolves how the December observations come in will shape the next decade of research in ways we can barely anticipate. If scenario A, natural but extreme, this is the least disruptive outcome. 3i Atlas joins the pantheon of weird but ultimately explicable objects, like Oumuamua before it, which created a stir with its elongated shape and lack of visible outgassing, but eventually fit into models of exotic asteroids or comets with unusual properties. The scientific takeaway: interstellar space is more diverse than we thought. Formation environments around other stars can produce objects with compositions and behaviors wildly different from what we see in our solar system. Carbon dioxide-rich comets exist. They behave oddly brightening, rapidly producing gas-heavy comas with minimal dust, accelerating efficiently due to some combination of favorable geometry and volatile chemistry.
They're rare, but not impossible. Models of planetary formation and cometary evolution are expanded to include this new parameter space. Textbooks add a chapter on interstellar visitors and their anomalous properties. PhD students write dissertations, analyzing 3i Atlas's composition and comparing it to other known objects. The public interest fades, the media moves on, and astronomers return to the steady work of cataloging the cosmos, slightly wiser and more humble about the universe's capacity for surprise. This is not a bad outcome. Science advances through incremental discoveries like this. Most breakthroughs aren't paradigm shifts. They're expansions, refinements, corrections. The universe reveals its complexity, one object at a time. If scenario B, no debris unknown mechanism. This is where things get interesting, and by interesting, I mean deeply unsettling for anyone who likes their physics clean and predictable.
If the December observations show no massive debris cloud, if the acceleration persists without commensurate mass loss, then we have a problem. A problem that can't be ignored or explained away with edge cases. We're forced to consider three broad possibilities. Possibility 1, new natural physics. There's some mechanism, some interaction between the comet and its environment that produces thrust without visible debris. Maybe it's exploiting radiation pressure in a way we didn't think possible, using the intense magnetic fields near the sun to accelerate charged particles and gain momentum through electromagnetic interactions. Maybe it's venting ultra-volatile materials that are genuinely invisible to our instruments. This would be exciting. Discovering new physics, new regimes, where known laws apply differently is the dream of every theorist. It means writing new papers, proposing new experiments, expanding our understanding of how the universe works. But it also means admitting that our models built on centuries of observation and calculation are incomplete. That there are phenomena we've missed, forces we haven't accounted for. It's humbling in the extreme. Possibility 2, measurement error. Very unlikely at this point. Maybe the whole thing is a mistake. The acceleration isn't real. The positional offset is an artifact of instrumental systematics or data analysis errors. This becomes increasingly unlikely as more independent observations confirm the anomaly. But mistakes happen. If someone finds the bug, if the offset disappears when recalculated using corrected methods, then we breathe a sigh of relief. It's embarrassing for the original team. There are uncomfortable conversations, but ultimately science self-corrects. The field learns. Better calibration protocols are developed. And 3i Atlas becomes a case study in the importance of skepticism and cross-checks.
Possibility 3, artificial origin. If natural explanations fail, if measurement errors are ruled out, then we're left staring at the possibility that 3i Atlas is not entirely natural, that it's at least partially engineered, that it's using a propulsion system deliberate, controlled, designed. This is the hypothesis that makes people uncomfortable because it implies intelligence. It implies technology. It implies that we're not alone and that whoever is out there has capabilities we don't. If this becomes the leading explanation, not because we want it to be true, but because the alternatives have been exhausted, then everything changes. CD gets a massive boost in funding and attention. Efforts to search for other similar objects intensify. Proposals for missions to intercept 3I Atlas or rendezvous with the next interstellar visitor are fast-tracked. The public response would be complicated. Some would be excited, others fearful. Conspiracy theories would flourish.
Governments would issue statements trying to manage the narrative, and the scientific community would be split, some embracing the possibility, others clinging to the hope that a natural explanation will emerge. It would be messy, contentious, emotional, because this isn't abstract theory. It's a question that touches on meaning, purpose, our place in the cosmos. If scenario C ambiguous and ongoing. This is the frustrating outcome, but probably the realistic one. Science rarely delivers clean answers on a schedule. If the data is ambiguous, some evidence for debris but not enough, some unusual features but not definitively artificial, then the community continues arguing. More observations are proposed. Different teams analyze the same data and reach different conclusions. 3I Atlas becomes a Rorschach test. What you see depends on your priors. If you think the universe is full of weird natural phenomena, you see a weird comet. If you think intelligence is common, you see a probe. This ambiguity could persist for years, until the next interstellar visitor arrives with similar properties, or until someone proposes an observation that definitively distinguishes between hypotheses. In the meantime, the object remains a puzzle. A tantalizing hint that we're missing something either about nature or about our neighbors among the stars.
Science is done by humans. And humans have emotions, biases, hopes, fears. Across the world, astronomers are preparing for the December observations. They're writing proposals, requesting telescope time, coordinating with colleagues in different time zones and different hemispheres. Some are excited, barely sleeping, checking weather forecasts for their observatories, obsessively hoping for clear skies. Some are nervous, worried that instrumental problems or clouds, or some unlucky coincidence will ruin their chance to contribute to solving this mystery. All are curious, driven by that fundamental human need to understand, to know, to answer the question that's hanging in the air like a held breath. For many, 3I Atlas represents the highlight of their careers. Not because they're chasing fame or headlines, but because it's genuinely fascinating. They became astronomers because they wanted to discover new things, to push the boundaries of knowledge, to be the first humans to understand something about the cosmos. Most astronomical research is incremental, measuring things more precisely, refining models, filling in small gaps in our understanding. Important work, certainly, but not paradigm shifting. 3I Atlas might be different. It might be the once-in-a-generation object that forces textbooks to be rewritten. The chance to study such an object, to contribute to solving its mysteries, is why they endured years of graduate school, why they work long nights at cold observatories, why they've dedicated their lives to this field. There's Avi Loeb at Harvard, who's been vocal about the possibility of artificial origins. He's controversial, willing to speculate publicly in ways that make more conservative scientists uncomfortable. Some colleagues think he's being reckless, that he's jumping to conclusions without sufficient evidence, that he's giving ammunition to conspiracy theorists and undermining the credibility of serious scientific inquiry. Others think he's being appropriately bold, that he's asking questions that need to be asked even if they're uncomfortable, that the history of science is full of paradigm shifts that began with someone willing to challenge orthodoxy. Loeb himself seems unbothered by the controversy. He's been through this before with Oumuamua, where his proposals about potential artificial origins generated both intense interest and fierce criticism. His position, as he's stated repeatedly in papers and interviews, is not that 3I Atlas is definitely artificial. His position is that we should at least investigate the possibility, that we shouldn't dismiss the idea without proper examination.
That the scientific method requires us to consider all hypotheses consistent with the data, test them rigorously, and let the evidence guide us. If it turns out to be natural, fine. We learned something about exotic comets, about the diversity of objects in the galaxy, about the limits of our models. But if it turns out to be something else, if we ignore the clues because we're too embarrassed to consider the implications, then we've failed as scientists. We've let our biases blind us to discovery, and that's the greater sin. For him, 3i Atlas is vindication, that considering uncomfortable possibilities is not just acceptable, but necessary. The anomalies are real. The questions are legitimate. Whether the answers turn out to be natural or otherwise, the process of asking, investigating, and testing is what science is all about. Then there are the comet specialists, researchers who've spent lifetimes studying these icy wanderers. For them, 3i Atlas is a challenge, an outlier that stretches their models to the breaking point. They're intimately familiar with how comets behave, how they brighten, how they produce jets, how outgassing affects their trajectories. They've seen weird comets before, objects that fragment unexpectedly, that produce unusual dust-to-gas ratios, that behave oddly due to quirks of composition or rotation. In most cases, with enough data and careful modeling, the weirdness resolves into something explainable. They're confident, maybe hopeful is a better word, that 3i Atlas will follow this pattern, that the December observations will reveal the debris cloud or will clarify the composition in a way that makes everything click into place, that they'll be able to publish a paper explaining this object using natural physics, showing that while it's extreme and unusual, it's not beyond the boundaries of what comets can do. This isn't stubbornness or closed-mindedness. It's a reasonable prior based on experience. Every other anomaly in cometary science has eventually yielded to natural explanation. Why should this be different? But there's also an edge of worry. Because if the debris isn't there, if the acceleration really can't be explained by natural outgassing, then they'll need to expand their models in ways they haven't anticipated. Or worse, acknowledge that maybe this object isn't a comet in the traditional sense, that it's something else wearing a comet's disguise. The astrometrists, scientists who specialize in precise position measurements are focused on the numbers. They're the ones who detected the 4 arcsecond offset, and they want to be absolutely certain it's real. They've gone through their calibrations again and again, checking for systematic errors, comparing against independent measurements from other facilities. They're confident in their results. The offset is real. But they're also aware that their measurements will be scrutinized intensely, especially if those measurements end up supporting an extraordinary claim. So they document everything, meticulously preserve all the raw data, make their analysis code available for others to check. Transparency is their shield against accusations of error or bias. For them, this is also deeply personal. Their reputations rest on their ability to measure positions accurately. If they've made a mistake, if the offset turns out to be an artifact of their analysis, it would be professionally devastating. But if they're right, if their measurements hold up under scrutiny and contribute to solving one of the great mysteries of the decade, it validates their entire approach, their methods, their careers. And then there are the SETI researchers who've spent decades searching for signals and finding silence. They've pointed radio telescopes at thousands of stars, listened across countless frequencies, searched for patterns that might indicate intelligence. And they've found nothing. Pulsars that looked promising turned out to be natural. Fast radio bursts sparked excitement but appeared to be astrophysical. The wow signal tantalized but never repeated. The silence has been discouraging. Not because they want to find aliens wanting isn't science, but because the continued absence of signals constrains their models and raises difficult questions. If technological civilizations are common, why the silence? If they're rare, what does that say about our own future? For SETI researchers, 3i Atlas is hope, a different approach to an old question. Maybe technosignatures don't look like radio broadcasts. Maybe they look like this subtle anomalies in the motion of interstellar objects, in their composition, in their behavior. Maybe we've been looking in the wrong place all along, listening for voices when we should have been watching for footprints. If 3i Atlas turns out to be artificial, and that's still a big if it would revolutionize SETI, it would say that the galaxy might be full of probes, small and quiet, exploring and observing. That intelligence might be detectable not through signals spanning light years, but through careful observation of objects passing through our own solar system. That would open entirely new research directions, new detection strategies, new questions about what we're looking for and how to find it. After decades of silence, a new conversation might finally begin. And then there's the public. People like you listening to this, people fascinated by the mystery, drawn to the question of whether we're alone, captivated by the possibility that something extraordinary might be happening in real time. The public response has been intense. Social media is full of speculation, excitement, fear. Hashtags trend. Reddit threads accumulate thousands of comments. YouTube videos with millions of views dissect every new observation, every published paper, every hint of information. Some see 3i Atlas as proof of aliens' final confirmation that we're not alone, evidence that's been covered up or ignored by mainstream science. They're ready to believe, perhaps too ready, seeing patterns and conspiracies where others see only uncertainty. Others dismiss it as hype, as sensationalism, as yet another alien probe story that will inevitably turn out to be a rock with unusual properties. They've heard it all before. Every few years, there's some new object or signal that gets people excited, and it always ends up being natural. They're skeptical, perhaps too skeptical, reflexively dismissing anything that sounds extraordinary. Most fall somewhere in between. Genuinely curious, wanting to understand, hoping for answers but willing to wait for evidence. These are the people who read the scientific papers even when they're dense and technical, who follow the astronomers on social media, who ask thoughtful questions and try to separate signal from noise. For all these people, 3i Atlas has become a symbol, a focal point for hopes and fears about contact, about discovery, about the future of humanity in a cosmos that might be stranger than we ever imagined. The optimists see it as the beginning of a new chapter. First contact won't be with motherships descending from orbit or radio signals carrying alien philosophies. It'll be subtle, gradual starting. With objects like this, visitors that make us wonder, that force us to question our assumptions, that hint at the presence of others without confirming it definitively. The fearful see it as a warning. If 3i Atlas is a probe, what are its intentions? Is it studying us, gathering data for some purpose we can't fathom? We've sent our own probes to other planets, and while our intentions are scientific, curious, benign, how would we appear to an alien intelligence observing our spacecraft? What conclusions would they draw about us? And if probes from other civilizations are common, passing through stellar systems, routinely gathering information, what does that say about the universe? Is it crowded with watchers, with explorers, with intelligences that have been studying their neighbors for millennia while maintaining silence? The philosophical implications ripple outward endlessly. If we're being observed, have we always been? Did probes visit Earth when dinosaurs roamed, when our ancestors first stood upright, when we built our first civilizations? Have they been watching our entire history, our triumphs and atrocities, recording everything for analysis by minds we can't comprehend? Or are we alone, and all this speculation is just our pattern-seeking brains, finding meaning in randomness, seeing intention where there's only chaos? The truth is, we don't know. And that uncertainty, that suspended state between knowing and not knowing, is profoundly uncomfortable for most people. We want answers. We want certainty. We want to know whether the universe is empty or full, whether we're alone or accompanied, whether the future holds contact or eternal solitude. 3i Atlas doesn't give us those answers. Not yet, maybe not ever. But it gives us something else, a focus for our questions, a concrete object to study, a puzzle to solve. And in the process of solving it, whether the answer turns out to be mundane or extraordinary, we learn, we grow, we expand our understanding of what's possible. That's why the December observations carry weight beyond their scientific importance. They're not just data, they're a referendum on possibilities on the questions humans have been asking since we first looked up at stars and wondered what else might be out there looking back. 3i Atlas doesn't exist in a vacuum. It's part of a larger tapestry of unsolved mysteries, strange coincidences and open questions that have accumulated over decades of astronomical observation. And let's connect some threads. The WOW signal. On August 15, 1977, a radio telescope at Ohio State University detected a strong narrowband signal lasting 72 seconds. The signal was so unusual that astronomer Jerry Amon circled it on the printout and wrote, "WOW" in the margin. The signal originated from the direction of the constellation Sagittarius near the star cluster M55. It matched the profile of an artificial transmission, narrow bandwidth, specific frequency, strong intensity. It's exactly what SETI researchers hope to find. The signal was detected at 1420 megahertz, the so-called water hole, a frequency band where galactic background noise is minimal and where many SETI searches focus. The choice of frequency seemed deliberate, as if someone was broadcasting on a channel where listeners would most likely be tuning in. The signal strength was remarkable, about 30 times stronger than the background noise. It rose sharply, plateaued, and fell off in a pattern consistent with a source that entered and then exited the telescope's beam as Earth rotated. Exactly what you'd expect from a stationary cosmic source being scanned by a rotating detector. It was never detected again. Despite repeated observations of the same region using more powerful instruments, the signal never repeated. Dozens of follow-up campaigns over the decades have found nothing. The source, whatever it was, went silent after those 72 seconds and has never spoken again. For decades, the WOW signal has remained unexplained. Debunking attempts have suggested comets, military satellites, terrestrial interference.
A 2017 study proposed that comets 266P Christensen and P2008Y2 Gibbs might have been in the right position to emit hydrogen clouds that could produce a signal at that frequency. But this explanation has been disputed. The signal characteristics don't quite match what hydrogen clouds would produce, and the probability of two comets being in exactly the right position seems low. Other explanations invoke satellites, aircraft ground-based transmitters reflecting off space debris. Each explanation has weaknesses. None have been definitive. The signal remains in that uncomfortable category of unexplained but probably natural. Now here's the connection. 3i Atlas arrived from roughly the same region of the sky, within about 9 degrees of where the WOW signal originated. 9 degrees is not a small angle. It's about 18 times the apparent diameter of the full moon.
In terrestrial terms, if you're looking at a distant mountain, 9 degrees is the difference between looking at the peak and looking at a point significantly down the slope. It's not precise alignment. But in the context of the entire celestial sphere, 41,253 square degrees covering the entire sky, 9 degrees represents a tiny fraction. It's 0.02% of the sky. And for a signal from 1977 and an object detected in 2025, separated by 48 years, the coincidence raises eyebrows. What are the odds? Hard to calculate precisely. The WOW signal's origin is uncertain. The error bars are large, perhaps several degrees, depending on how you account for the telescope's beam pattern and calibration uncertainties. And 3i Atlas's trajectory traces back through interstellar space, but pinpointing its exact origin requires assumptions about how long it's been traveling and whether gravitational perturbations from unseen masses altered its path.
Still, the coincidence is noted in the scientific literature. Papers analyzing 3i Atlas mention the proximity to the WOW signal source. Some researchers dismiss it as meaningless, a random coincidence in a universe full of random coincidences.
Others suggest it's worth considering if you were an advanced civilization sending both a signal and a probe, you might send them from the same star system. The signal announces your presence. The probe studies neighbors who might respond, or perhaps the signal and the probe are unrelated, but both originate from the same stellar neighborhood, a region of space that happens to harbor multiple interesting phenomena. Maybe there's something about that region we don't understand. Maybe it's where a dense cluster of stars or an unusual interstellar environment produces both strange radio emissions and unusual objects, or it's pure chance. Two unrelated mysteries that happen to intersect in space and time with no connection except our human tendency to see patterns in randomness. Either way, it's another data point in the larger puzzle. Another thread in the web connecting 3II Atlas to decades of unexplained observations, unanswered questions, and the persistent nagging feeling that maybe, just maybe, we're not seeing the full picture. Oumuamua's mysteries. In 2017, the first confirmed interstellar object, 1Y Oumuamua, sparked its own controversy. The object was elongated, tumbling rapidly, and showed no visible comet-like activity despite passing close to the Sun. Avi Loeb and colleagues proposed that Oumuamua might be an artificial light sail based on its unusual acceleration that couldn't be fully explained by outgassing since no coma was detected. The mainstream explanation eventually settled on exotic outgassing of hydrogen ice, too faint to see, but sufficient to produce the observed acceleration. It's a stretch, but it fits the data. But Oumuamua was the first. Now we have 3 interstellar objects. Borisov behaved like a normal comet. 3I Atlas is anomalous in different ways. Composition, trajectory, the 10th anomaly. Are these objects related? Is there a population of interstellar visitors, some natural and some not? Or is Oumuamua natural, 3I Atlas natural, and we're just seeing the diversity of what the galaxy produces, pattern or noise, signal or coincidence? The more data we gather, the closer we'll get to an answer. The Fermi paradox. Enrico Fermi famously asked, "Where is everybody?" If intelligent life is common in the galaxy, and if technological civilizations inevitably spread through space, then why haven't we seen evidence of them? The paradox has spawned dozens of proposed solutions. Maybe intelligence is rare. Maybe civilizations self-destruct. Maybe they're hiding. Maybe interstellar travel is impossible. Or maybe we're looking in the wrong places.
If technosignatures aren't megastructures or radio signals, but subtle anomalies in the behavior of small objects, then SETI has been listening for the wrong thing. We've been searching for signals when we should have been watching for objects that move wrong. 3I Atlas might be the first clue that the Fermi paradox resolves not with "they don't exist," but with "we didn't recognize them." The Drake equation. Frank Drake's famous equation estimates the number of active communicative civilizations in the galaxy. It's a product of factors: star formation, rate, fraction of stars, with planets, fraction of planets that develop life, fraction that develop intelligence, fraction that develop technology, capable of communication, and the lifetime of such civilizations. The uncertainties are enormous. Depending on what values you plug in, you get answers ranging from "we're alone" to "millions of civilizations." One of the biggest uncertainties is the lifetime factor. How long do civilizations last? If they typically destroy themselves within centuries of developing technology, the galaxy might be full of ruins, but empty of active intelligences. But what if civilizations don't communicate with radio signals? What if they send probes instead, patient, slow-moving explorers that traverse the galaxy over millions of years, gathering data, mapping the terrain? In that case, the Drake equation might need a new factor: the fraction of civilizations that explore via probes rather than signals. And the detection method shifts from listening to watching. 3I Atlas, if artificial, would be a data point for that factor. Proof that at least one civilization chose the probe route. And if one did, others might have too. all of these mysteries. Wow signal, Oumuamua Fermi paradox. Drake equation are connected by a common thread, the question of whether we're alone and how we'd know if we weren't. CI Atlas sits at the intersection.
It's not definitive proof of anything, but it's a hint, a whisper, a suggestion that maybe, just maybe, the universe is more populated than the silence suggests. There's a fine line between responsible speculation and conspiratorial thinking, between being open-minded and being gullible, between following the data and seeing patterns that aren't there. Science walks that line every day, and the 3i Atlas case is a masterclass in how to do it right and how easy it is to slip into error. What responsible speculation looks like. Acknowledge uncertainty. Real scientists admit when they don't know. They use qualifiers, possibly and potentially. One hypothesis suggests this is speculative. Avi Loeb's papers on 3i Atlas are careful to frame artificial origins as one hypothesis among several, not as a conclusion. He presents the anomalies, calculates probabilities, and says, given the low probability of all these features occurring naturally, we should at least investigate the possibility that this object is not entirely natural. That's responsible. It's not claiming certainty. It's saying, the data is weird.
Let's consider all explanations, including uncomfortable ones. Follow the data. Speculation grounded in measurements, observations, and calculations is different from speculation based on wishful thinking or fear. The 10th anomaly is real. The 4 arcsecond offset is measured by multiple instruments. The momentum mismatch is calculated using basic physics. These aren't opinions, they're facts that need explanation. Starting from data and working toward hypotheses is the scientific method. Starting from a belief and cherry-picking data to support it is confirmation bias. Testable predictions. Good hypotheses make predictions that can be tested. If X is true, we should observe Y. If 3i Atlas is venting ultra-volatile ices, we should detect specific spectroscopic signatures in the infrared. If it's using radiation pressure, the acceleration should continue in a predictable way. If it's artificial, there might be patterns in brightness or emissions. Each hypothesis makes predictions. The December observations will test those predictions. Hypotheses that fail are discarded. Hypotheses that succeed are retained. That's how science works. Peer review speculation is not published in a blog post and declared true. It's submitted to journals, reviewed by experts, criticized, defended, and eventually accepted or rejected by the community. The papers analyzing 3i Atlas have gone through peer review. Other scientists have examined the data, checked the calculations, and pointed out weaknesses. This process filters out errors and ensures that published claims have some credibility. It's not perfect. Peer review can be biased. Reviewers can miss mistakes, but it's better than the alternative unfiltered claims with no accountability. What irresponsible speculation looks like. Claiming certainty. 3i Atlas is definitely an alien probe. No, we don't know that. The data is ambiguous.
Making definitive claims without definitive evidence is dishonest. Ignoring context. Cherry-picking anomalies while ignoring the broader picture. Yes, 3i Atlas has 9 confirmed oddities, but thousands of other comets and asteroids have 0 oddities. You can't focus on one weird object and claim it represents the norm. Conspiracy thinking, governments are hiding the truth. Maybe. Or maybe the data is being analyzed carefully before release. Or maybe there's nothing to hide. Assuming conspiracy without evidence is lazy thinking. Motivated reasoning. Believing something because you want it to be true, not because the evidence supports it. If you desperately want aliens to exist, you'll see aliens everywhere. If you desperately want them not to exist, you'll dismiss anomalies. Good science requires emotional detachment. You follow where the data leads, even if it's not where you hoped. Why this balance matters. The public watches how scientists handle mysteries like Three-Eye Atlas. If we're too conservative dismissing anomalies without investigation, we risk missing genuine discoveries. If we're too speculative jumping to conclusions without evidence, we lose credibility. The balance is delicate. Acknowledge that something is weird. Investigate thoroughly. Consider all hypotheses, even uncomfortable ones, but don't claim answers we don't have. That's what the scientific community is trying to do with Three-Eye Atlas. And so far, despite the sensational headlines and social media speculation, the process is working. The data is being gathered, the hypotheses are being tested, and we're getting closer to an answer.
We're in the waiting period now, the liminal space between question and answer, between mystery and resolution. December 19th, 2025 approaches. Telescopes are pointed, instruments are calibrated, data is being collected even as you hear these words. And somewhere in that data, in spectra and images and positional measurements, the answer waits. Let's recap what we know for certain. Three-Eye Atlas is real. It's the third confirmed interstellar object to pass through our solar system. It was discovered on July 2025 and reached perihelion on October 29, 2025. It has 9 documented anomalies: ecliptic alignment, planetary encounter, timing, conjunction, hiding backwards, composition, water deficit, extreme polarization, explosive brightening blue color, and sun-facing jets. Each is independently measured. Each is statistically improbable. Together, they form a pattern that sets this object apart from every comet we've seen before. And then there's the 10th anomaly, the acceleration without visible debris, the 4 arcsecond positional offset that demands an explanation. The mismatch between observed force and observed reaction mass. The December 2025 observations will test whether the debris exists but was hidden, whether some exotic mechanism explains the acceleration, whether we made a mistake, or whether we're confronting something genuinely unprecedented. Let's also acknowledge what we don't know. We don't know the exact mass of Three-Eye Atlas. We don't know its precise composition or internal structure. We don't know how much material it actually ejected during perihelion, only what we can see, which might not be everything. We don't know whether the acceleration is a one-time event or ongoing. We don't know whether other interstellar objects show similar properties or whether Three-Eye Atlas is unique. And we don't know not yet whether the explanation is natural or something else. Those uncertainties are not weaknesses.
They're the fuel of science. They're what drives the next observation, the next calculation, the next hypothesis. Certainty ends inquiry, mystery propels it. So what do we do while we wait? We stay curious. We resist the urge to jump to conclusions. We acknowledge that the universe is under no obligation to be simple or familiar or comfortable. We recognize that most astronomical anomalies have turned out to be natural. Pulsars, quasars, gamma-ray bursts, all initially mysterious. All ultimately explained by physics we already knew or could figure out. The track record says, bet on nature. When pulsars were first discovered in 1967, the signals were so regular, pulsing with such precise timing, that astronomers briefly considered whether they might be artificial beacons. They even jokingly called them LGM-1, LGM-2, etc., where LGM stood for Little Green Men. But within months, the natural explanation emerged: rotating neutron stars with magnetic fields, sweeping beams of radiation across space like cosmic lighthouses. Nature, not intelligence. Fast radio bursts first detected in 2007 were similarly puzzling. Powerful radio pulses lasting just milliseconds coming from distant galaxies with no obvious source. Their short duration and high energy led to speculation about everything from neutron star collisions to alien transmitters. But as more were detected and studied, natural explanations emerged, likely involving magnetars, highly magnetized neutron stars undergoing catastrophic magnetic field reorganizations. Again, nature. The history of astronomy is full of these moments. mysterious signals that turn out to have mundane explanations. Anomalies that upon further study fit neatly into our understanding of physics. The universe is strange, but it's not usually artificial. But we also recognize that history is full of surprises. Every generation thinks they understand the universe, and every generation is humbled by the next discovery. The universe has layers, complexities, regimes we haven't explored. Maybe 3i Atlas is teaching us about one of those regimes. Newton thought he'd explained motion. Then Einstein showed that at high speeds and strong gravity, Newton's laws are approximations. Quantum mechanics revealed that at small scales, classical physics breaks down. Who's to say there aren't other regimes, other corners of parameter space where our current understanding is incomplete? Maybe objects moving through interstellar space for millions of years, subjected to cosmic rays and magnetic fields we can barely measure, develop properties we haven't anticipated. Maybe the interaction between a comet and the solar wind at precisely the point where 3i Atlas passed through creates effects we've never modeled. Maybe there are phenomena waiting to be discovered in the space between the equations we've already written. Or maybe, and this is the possibility that makes hearts race and skeptics scoff, maybe it's teaching us that we're not alone. The silence of the universe has been our constant companion. We've grown accustomed to it. We've built philosophies around it. Some find comfort in the solitude we're special because we're alone, significant because no one else is watching. Others find it existentially terrifying. All this vastness, all these stars, and nowhere else is there a mind like ours wondering about its place.
But what if the silence is just our failure to recognize the voices? What if intelligence doesn't announce itself with radio signals or megastructures, but with subtlety, with objects that move almost naturally, but not quite, with anomalies that whisper rather than shout? If that's the case, then 3i Atlas might be the first word we've understood. In a conversation that's been happening all around us in a language we're only now learning to speak. Or maybe not. Maybe it's just a weird rock from a weird place behaving weirdly because the universe is weirder than we gave it credit for. Time will tell. December will tell. And we wait knowing that the answer, whatever it is, will teach us something. Will push the boundaries of knowledge in one direction or another. Will either confirm that nature is stranger than we thought or suggest that nature isn't the only game in town. That uncertainty, that suspended moment between question and answer, is where science lives. Not in the knowing, but in the asking. Not in the destination, but in the journey toward it. And 3i Atlas is taking us on quite a journey. Here's the uncomfortable truth: we may not get a clean answer. The December data might be ambiguous. The debate might continue for years. 3i Atlas might remain a mystery filed alongside Oumuamua and the WOW signal in the category of things we can't quite explain. And that's okay. Science doesn't promise tidy resolutions. It promises progress. Each observation, each measurement, each hypothesis tested brings us closer to understanding. Whether 3i Atlas is a natural comet with extreme properties or an object using physics we don't understand, or however unlikely evidence of extraterrestrial intelligence, it's expanding our knowledge. It's forcing us to think harder, look closer, question assumptions. That's valuable regardless of the answer. But let me leave you with the question that haunts this entire story.
The question that makes the 10th Anomaly more than just a scientific puzzle. The question that touches on meaning and purpose and our place in the cosmos. If 3i Atlas changed its course once without visible cause, what's to stop it from changing course again? And if it can, if objects from between the stars can alter their trajectories at will, maneuvering through the solar system with intention rather than randomness, what does that mean for every assumption we've made about what's natural, what's possible, and whether we're truly alone in watching the cosmos? The universe waits patiently. Answers come to those who watch, measure, and refuse to look away. December 19th, 2025. Mark the date. The story continues, and we'll be watching.